So I have the great pleasure of hosting Professor John Moffat. So Professor Moffat, thank you for your time and for doing this podcast.
Thank you for having me on the podcast.
Wonderful. So my first question would be what inspired you to challenge the dominant interpretations of general relativity and quantum mechanics?
Well, general relativity is one of the remarkable feats in physics, and it works extremely well for the solar system and beyond the solar system, all the way out to the Kuiper belt and beyond. But when you go up to beyond to galaxies and clusters of galaxies and cosmology, it only fits data if you postulate dark matter and dark energy, which have not been observed directly. So there are two possible ways of looking at this. One is to think that eventually dark matter will be directly tested. They will detect a dark matter particle. And the other is that dark matter doesn't exist and you have to modify Einstein's general relativity.
And do you think mainstream physicists are too rigid in their acceptance of Einstein's theories?
Yeah, the community accepts Einstein's theories, and the major part of the physics community accepts dark matter. Dark energy is responsible for the acceleration of the expansion of the universe. So that's a separate issue. Again, it's not it's controversial whether you can detect the so-called dark energy, but the dark matter and dark energy are part of what's called the standard model of cosmology, and it does fit the data very well. However, it's not been they have not been detected. The dark energy is presently described by the cosmological constant, which was added by Einstein to his field equations in 1917 when he published the first paper on cosmology. Actually, one of the pioneering papers on cosmology, and this cosmological constant is now chosen to be responsible for dark energy. But recent data from from what's called DAISY, Dark Energy Survey observations, uh, seems to have indicated that there could be a deviation from the cosmological constant, from a constant dark energy.
So, how do you respond to critics that say your modified gravity theory lacks sufficient empirical support?
All right, so in 1983, uh, the MOND, so called, was published, and it's a modified Newtonian dynamics. And this was the first Israeli physicist, the first paper to propose that instead of dark matter, you have modified gravity. However, it's not been entirely successful in making it a relativistic theory. It's a Newtonian gravity theory, although attempts have been made to make it relativistic. it fits galaxies quite well. It doesn't fit clusters of galaxies. That's large collections of galaxies. And it doesn't do too well with cosmology. Whereas my modified gravity theory called scalar tensor vector gravity, otherwise known as MOG. MOG stands for modified gravity, or privately for Moffat gravity. As there are now many papers published by myself and two collaborators, Victor Toth and Martin Green, and some other collaborators recently, and many other papers fitting data. It fits galaxy data, cluster data, and cosmological data. In particular, papers have been published showing how it fits what's called the cosmic microwave background spectrum, and also the late time power spectrum, where the late time power spectrum determines the correlation between pairs of galaxies. It, it determines experimentally the distribution of galaxies in late time cosmology.
And do you think your theories have been unfairly marginalized by the scientific world?
Well, the Milgrams, this is the Israeli physicist who published Modified Newtonian Dynamics. Mond is a non-relativistic theory, like Newton, whereas my theory is based on Einstein gravity. It contains Einstein gravity in the limit of non-relativistic weak gravity. So you have to have a modified gravity that's consistent with Einstein gravity, because Einstein gravity is very successful for fitting solar system data. If your modified gravity doesn't fit the solar system data, then it's wrong. So, as for the marginalization, it's more complicated than Einstein gravity, mathematically speaking. It has to be, because you have to introduce extra degrees of freedom. Uh, for example, a vector field, a vector gravity field is introduced in addition to the metric of space-time underlying Einstein's theory based on Riemannian or pseudo-Riemannian geometry. So it's more difficult for people to work with my theory as compared to Milgram's Mond, and this marginalizes it for some physicists.
And you wrote a memoir called Einstein Wrote Back that documents your encounters with various other famous physicists like Niels Bohr, Einstein, Schrödinger, Pauli, Dirac, Oppenheimer. So, can you tell us some interesting stories from your encounters with them?
Yes, well, maybe I should just quickly uh, talk about my early history as far as becoming a physicist is concerned. I started as an artist, went to Paris in 1917, in 1947, and studied with a Russian French artist, painter, abstract painter called Serge Polyakov. He was my mentor. So I was in Paris for a year, and I exhibited paintings in several international art shows in Paris. Then I went back to Copenhagen and started reading popular books on physics, particularly Arthur Eddington's books on popular physics books. So I decided this was interesting, and maybe I should learn maths and physics. I left school when I was 16, and so at home I learned maths and physics. It turns out I was what one might call an autodidact, a self-learner. And within a year or so, I did equivalent of 4 years of undergraduate physics and maths. So I got up to the point where I was studying Einstein's, gravity theory, general relativity, and his unified theory, which he was working on at the time. So I found reasons to criticize what he was doing. So I wrote 2 papers and sent them to Einstein in Princeton, and never expected to hear from him, but I did. And he wrote me letters in German and took my criticisms seriously. and this led to a correspondence with Einstein over a period of 6 months. And so Niels Bohr got to hear about this at the Bohr Institute in Copenhagen, and he invited me to the institute, and I was interviewed by Niels Bohr for 2 hours, and this led to my giving a talk at the institute about my papers. But Einstein's work on unified theory was not popular with physicists at the time. So I've had to defend Einstein during my talk. and Bohr was not complimentary towards Einstein about what he was doing. He called him, Moffat, do you realize that Albert is an alchemist? He's trying to turn lead into gold, metaphorically speaking, in his physics. Anyway, so the Bohr contacted the British government, and who invited me to England, where I was sent around to professors to see whether I was a genuine article or not. And one of the professors I visited was Erwin Schrödinger in Dublin, and I spent 2 days in his house, and we talked physics. And there are interesting stories attached to that. But anyway, he wrote a letter of recommendation, which I never read, but then the British government, on the basis of this letter, sent me to Cambridge University. And I met with Dennis Sharma, who was a fellow of Trinity College, Cambridge, cosmologist, famous cosmologist. And Sharma talked to me about my work and said, we're going to make you a PhD student at Trinity. So he took me to the bursar at Trinity College and said, this John Moffat is now a PhD student at Trinity. But this person said that, but Moffat doesn't have an undergraduate degree. Never mind that, he's going to be a student, okay? So Fred Hoyle was chosen as my supervisor, professor. Fred Hoyle, famous for inventing the Big Bang words, and he. So then I went to see Fred Hoyle, and he said, "You haven't done any undergraduate work. Maybe you should take the tripos exam at part 2 at Cambridge." So, being 20 years old or so, opportunistic possibly, I said, "Well, this is just a waste of my time, and I should proceed with the PhD as is." So I decided to resolve this problem. So I wrote 3 papers on gravity, and actually my first modified gravity theory, and published 3 papers in the Cambridge Philosophical Society proceedings. All 3 were accepted. And so I went back to Fred Hoyle with the papers. He said, and he read them. He said, "Forget about the tripos. Continue as you were." So then, 4 years later, I got my PhD. I was possibly the first, I'm not sure about this, but to obtain a PhD at Trinity College without an undergraduate degree. So then I went then I was made a fellow of Imperial College London, and the professor there, Abdus Salam, took me in as a postdoctoral fellow. And actually, he was my supervisor at Cambridge because Fred Hoyle went to Pasadena, California Institute of Technology. So I had to get another supervisor. So that's a brief story about my beginnings as a physicist.
Wonderful. Thank you for sharing. So my next question is: should physics give up the search for a unified theory if it continues to hit dead ends?
Well, I did continue with the unified theory subsequently when I got to the States. I became a member of a research institute in Maryland, Baltimore, called RIAS, Research Institute for Advanced Study. And I was made a senior research physicist there. They had a collection of well-known physicists and mathematicians. And so I was there for 6 years. And I also spent time at the Institute for Advanced Studies in Princeton during that time. However, when I got to in Cambridge, I not only worked on gravity, because Abdus Salam was doing research on particle physics. So I switched to particle physics as well as doing gravity for my PhD thesis. And so when I got to RIAS, a so-called Research Institute in Baltimore, I did research on particle physics and published several papers in particle physics at the time. Then eventually, after 6 years at this institute, I was offered a position as professor, University of Toronto, Canada. And I ended up there as an associate professor. I skipped assistant professorship. I got associate professorship with tenure, and I became a full professor within about a year. And there I stayed until I retired in 1997, after which I came to the Premier Institute as a research member. And here I am. I'm also an adjunct professor at the University of Waterloo.
And how do you handle the existential implications of a universe without dark matter?
So it, it's a strange situation with dark matter. It was first proposed by the Swiss astronomer called Zwicky, Fritz Zwicky, in 1931, because he studied the stability of the Virgo cluster of many galaxies, and discovered by using what's called the virial theorem, the stability of kinetic energy and potential energy for bound objects, galaxies in this case, that the Coma cluster was not stable. There wasn't enough gravity. Gravity was not strong enough. So he proposed that there had to be extra matter. He called it dunkle Materie. It's German for dark matter. And so it went. But his work was pretty well ignored until the work research by the astronomer Vera Rubin and her collaborators in the late 60s and 70s. So what they did was to determine the speed of galaxies going around in external galaxies, that is. And by measuring the speed of the gas, hydrogen gas, you can't see the stars individually in galaxies. They're too far away. But the stars make the galaxy bright, of course. So they discovered that the speed of the stars was much slower than what Newtonian gravity predicted. One should say that the gravity theory of galaxies is weak. So Newtonian gravity works very well. And you can more or less ignore the corrections due to Einstein gravity for galaxies. And so what they did, what they found was that the speed of the stars going around in the galaxy is determined by what's called the rotation curve. This is a curve that shows you the speed of the galaxies. And it's a curve which is a function of the distance from the center of the galaxy. And these rotation curves were flat, not coming down in what's called a Newtonian Kepler orbit, which is quite a decline of the rotation curve. So many observations have been done since then. And the conclusion is that you have to explain the difference between the flatness of the rotation curves and Newtonian gravity. So the easiest way to do that is to postulate dark matter. So in Einstein's field equations, you have a left-hand side which describes the geometry of space-time, and on the right-hand side, you have what's called the energy momentum tensor. It describes matter. So you throw in more matter into the energy momentum tensor, and you get stronger gravity on the left-hand side. and then you get a flat rotation curve. However, the dark matter has to be detected, because in physics you have a theory, hypothesis, and then you have to test the theory, hypothesis with experiment. This is how you do physics. So in the case of dark matter, you have to detect the particles that make up dark matter, if indeed there are particles. And we've now been trying to detect these particles for about 40, 50 years without any success. So in the case of modified gravity, my gravity theory makes the Newtonian gravitational constant, which occurs in Einstein's gravity theory, and also in Newtonian gravity, of course. And the inverse square law of Newtonian gravity is proportional to the cosmology, to the gravitational constant. So I make the gravitational constant vary, so you can have a stronger gravity, only using ordinary matter. And the ordinary matter consists of protons and electrons in galaxies, cosmology. We're made of, so the budget in dark matter models, the budget for the matter and energy is 5% me, protons and electrons. Some 30%, 25, 26% for dark matter, and the rest, 70-some percent, is the dark energy, which, as I mentioned, is responsible for the acceleration of the expansion of the universe. That's the whole matter budget. So it's disturbing that we are only 5% like ghosts in the whole matter of the universe, and the rest is dark. The dark means that dark matter does not interact with electromagnetism. It's dark. Nor does it interact with the protons and electrons and quarks made of that make up protons or whatever, the ordinary matter, because we don't detect it yet. So my position is we should continue to look for dark matter. And because if they do detect these particles, then, and it fits the data, then forget about modified gravity. Einstein's gravity theory is beautiful and simple. On the other hand, if they don't detect it, the only alternative is modifying Einstein gravity. But you don't modify some theory like Einstein gravity easily. It's a paradigm shift. And physics is conservative, as it should be. You don't accept a paradigm shift unless the data really compels you to do so. And it takes time to obtain enough data to reinforce the paradigm shift. That's the status. So personally, what do I think personally about it? I don't think they're going to detect dark matter. That's my personal opinion, for what it's worth. So the dark matter consists of two kinds of detections. There's what's called WIMPs, weakly interacting massive particles. These are heavy particles, several billion electron volts, much heavier than the proton, which is 1 billion electron volts in energy. And there's been considerable amount of effort to detect these WIMPs, weakly intermassive particles, unsuccessfully so far. Underground experiments, for example, using large tanks of xenon gas, it's an inert gas, and the nuclei in this gas are supposed to interact with the dark matter particles and show a signal. No such signal has been detected. So what's happened to these experiments now is that they've reached a cross section for the WIMPs interacting with nuclei, which is getting close to what's called the neutrino fog. Neutrinos. The neutrino fog, neutrinos are everywhere, also in this gas, xenon gas. And the neutrino fog is such that the noise of the fog makes it no longer possible to do these experiments. So now they switched to what's called axions. These are ultralight dark matter particles. And these particles can reach very small masses, even down to 10 to the power minus 22 electron volts. The electron's mass is 500,000 electron volts. So you're going way down to 10 to the power minus 22 electron volts. This is a huge range to look for these particles. So ongoing experiments are trying to detect axions.
And do you believe string theory has distracted physics from more promising directions?
Yes, well, string theory has been going now since 1975. And it has been, in my opinion, not successful. I'm about to make controversial statements. The problem is that what they're saying is that in the standard model of particle physics, particles like the quarks, electrons, and leptons, the Higgs particle, are point particles. They're elementary particles described by points in what's called local quantum field theory, which is the language of particle physics. And string theory says that they're not points, they're strings. And early on in the string theory ideas, one of the strings describing a particle described a graviton. A graviton is the quantum particle of quantum gravity, the equivalent of the photon in electromagnetism. It's what's called a spin 2 boson. The photon is a spin 1 boson. So people claim that this is an important discovery. And Edward Witten, who has done considerable research in string theory, claims still today that this is an important discovery in the sense that string theory explains the reason why gravity exists. However, there are three criticisms of string theory. It's not been tested experimentally. It's very difficult to test it because the string theory tests are expected to occur at very high energies. In some cases, close to what's called the Planck energy. Planck energy is determined by Planck's constant, the gravitational constant, and the speed of light. And this Planck energy is about 10 to the 19 GeV, billion electron volts, which is way beyond any accelerator that you can ever build. You need an accelerator the size of the Milky Way galaxy to detect the string theory in this sense. The other problem is that the string theory is formulated in high dimensions, 10 dimensions, 11 dimensions. In particular, space-time is 4 dimensions, 3 space and 1 time. So you need 6 extra spatial dimensions, over and above the dimensions of the space-time that we live in, that we observe, which is 4, 3 spatial plus 1 time. So without 10 dimensions, the theory is not mathematically consistent. However, to do observational physics, you have to compactify the 10 dimensions to 4 space-time dimensions. You compactify it. And there's a semi-infinite number of ways of doing this. One popular way is to do Calabi-Yau compactification. But it's claimed that there are 10 to the power 500 Calabi-Yau compactifications possible. This is a huge, what's called landscape of string theories. And all these theories, landscape theories, have different vacuum states, the lowest ground state of energy. So there are many string theories. And the third problem is that to make string theory mathematically consistent, you need supersymmetry. And supersymmetry was invented years ago. And in supersymmetry, effectively you have what's called supersymmetric particle partners. So every boson particle, the photon, has a supersymmetric fermion particle. A fermion is a spin-and-a-half particle. Bosons are spin 1 or 2. And they've been trying to detect supersymmetry at the CERN Large Hadron Collider for years. And the result is that up to 14 TeV, 13, 14 TeV, trillion electron volts at the CERN Large Hadron Collider. No, they have not detected supersymmetry. So you have to keep going to higher energies above accelerator energies and claim, well, they exist at higher energies. Supersymmetric superpartner exists at higher energies. But this is not a good situation. So string theory continues to be researched. And there's no reason it shouldn't be, I mean, in spite of the difficulties. But there's less research now being done in string theory than, for example, in the 1980s, which was a dominant research. So since the 1990s, late 1991, I published an alternative quantum field theory. In quantum field theory, you explain particle interactions with what's called local quantum field theory. And local quantum field theory, the interactions occur at a point locally. However, so when you do local quantum field theory, you describe the vertex of interaction between particles with a Dirac delta function. This is the simplest distribution at the vertex. It's a distribution. It's called test function distribution. However, when you introduce this Dirac delta function, the theory produces infinities, because when you calculate quantum corrections by what's called Feynman diagram loops, they are divergent. So you have to renormalize, you have to cancel one infinity by another. And this has been successful for particle physics. String theory claims that the theory is finite. This has been still controversial whether there's a rigorous proof of finiteness, but you can see why it can be finite, because a string replaces a point. So this can get rid of the infinities. However, I published this quantum field theory called non-local quantum field theory. So instead of a Dirac delta function at the vertex of interaction of two particles, three particles, I have what's called an entire function distribution. And this distribution allows you to make the so-called loop quantum particle interactions finite in what's called perturbation theory. And the renormalization of perturbation theory calculations becomes finite. So there have been many papers published about this, also by others. And it can also be applied to quantum gravity, because Einstein's quantum gravity is not renormalizable. Has been a reason for serious problems with quantum gravity since for many years. So this makes quantum field theory a finite theory. However, again, it becomes marginalized, because the standard theory of renormalization is entrenched in the physics community, in textbooks and so on. So, however, it's not exactly a paradigm shift, but it's a big shift in the technical way you approach quantum field theory.
What are your thoughts on the multiverse hypothesis?
You asked me to talk about controversial questions, which is very good. I appreciate this. However, multiverse is not, in my opinion, physics. It's metaphysics. Because it's not clear you can ever detect a multiverse. If you can't, as I get back to the beginning, when you do physics, there are two parts to doing physics. The first part is to have, well, we are trying to describe nature. Okay, that's what physics does. So the first part is to have an idea, hypothesis, about some physics issue. And then the next part is to, well, there are actually three parts. The next part is to form a mathematics that can describe your hypothesis. And the third part is to test the theory. And this is where the difficulty comes in. Because if it doesn't pass experimental tests, it's wrong, and you throw it away and start over. And physicists have difficulty in throwing away ideas they've worked on, often a whole career based on some physics theory. It's, it's hard to say that your child, physics theory child, is actually misbehaving and not agreeing with experiments. So I have a saying about it. Physics is imagination in a straitjacket. You need the imagination, hypothesis, theory, and you need a straitjacket, which is experimental data, to test the theory. And this last part is very hard to deal with. By the way, I should some of the papers I've been publishing recently. So one paper I've publishing with two collaborators, um, Victor Toth, who's been a long time collaborator of mine in physics, and a young student who's now at Cambridge University, Hunter Sharon. He just did his undergraduate degree at McMaster University and said he wanted to do research with me. So he got brought into this problem. And this issue is that the Milky Way, our galaxy, has a rotation curve, as we discussed earlier. And there's been ongoing effort for years to determine this rotation curve. Is it flat or does it agree with Newtonian gravity? So data has come out called the Gaia data. Gaia data, and it's the third release of the data. There are 5 releases in all. And this data has been published in 5 papers by top astronomers. And what they discovered is that the data shows that the rotation curve for the Milky Way is not flat, it's declining by what's called a sharp Keplerian decline, which follows Newtonian gravity. But this is very disturbing because it doesn't agree with the general physics scenario that all the rotation curves are flat. So this is a controversial issue. And I put out this paper, and we put out this paper, showing how the rotation curve is not flat. So it doesn't allow for what's called a dark matter halo, which is supposed to be a halo encircling all galaxies. And I spent some months after the data was published in 4 or 5 papers, worrying about this and deciding whether I should do something about it or not. Because I personally didn't understand the consequences of this. And decided that we should publish a paper, which is, again, possibly which can be marginalized, because again, it goes against the current of physics. By the way, you can't just fit galaxies and clusters of galaxies with a modified gravity theory. You've got to fit the cosmological data, which is there's a large amount of cosmological data now. When I was a student at Cambridge, there was little data for cosmology. It was considered a mathematical physics problem. And now it's quite remarkable how we've learned so much about the universe. It's quite extraordinary. Recently, I published publishing papers on quantum gravity. The big problem with quantum gravity has been going as a searching for quantum gravity or discussing quantum gravity 100 years, ever since the beginnings of quantum mechanics, quantum physics in the 20s. And the problem is that there are no quantum gravity data. So you can't test quantum gravity. And there are many quantum gravity models that have built over the years, dozens, including my own, by the way. And in my non-local quantum field theory, which by the way is strictly causal, I can prove it's strictly causal as local quantum field theory. That the quantum gravity is finite. So you don't have to worry about infinities. So I can produce a cross section for interaction of two gravitons or graviton with matter, but I can't test it. There are no data. So I'm stuck with the lack of a straitjacket, as mentioned earlier. Anyway, recently I got back into quantum gravity, trying to understand whether gravitons, which are the equivalent of photons in quantum gravity, can be consistent with gravitational data. So in a paper I'm just been accepted for publication, I used the LIGO Virgo Kagra gravitational wave data. So there, what you have is two black holes merging billions of light years away. And they merge into one big black hole and spiral in and merge. And they generate enormous amounts of energy in the form of gravitational waves. So you take the amount of gravitational energy generated by the merging of these black holes, which in fact turns out to be 3 times the mass of the sun times the square of the velocity of light, E equals mc squared. And you work it out, it's 10 to the power 47 joules. You measure energy in joules. So then you take the energy of one graviton, which is E equals Planck's constant times the frequency, hf. And the frequency is 200 hertz from the LIGO experiment, the first experiment, which is GW 190514, 2014, the first detection of gravitational waves. And you divide the energy of one graviton into the total energy emitted, and you get 10 to the power 78 gravitons. That's a huge number of gravitons. So the question then is, if you treat the gravitational energy, the gravitational waves, as a coherent gravitational wave, coherent, and the gravitons is a coherent collection of gravitons, like a laser beam, which in fact is the truth, because gravitational waves are very strong, coherent. Then it turns out that I can take my 10 to the 78 gravitons, and I can use the, the, the LIGO experiment consists of two arms perpendicular to one another with mirrors attached. And the gravitational wave goes by the arms and displaces the size of the arm. Delta L. L is the length of the arm, which is 4 kilometers. So the displacement is called delta L. You divide by the length L, and you get a number. It's called the strain. It's 10 to the power minus 21. Delta L over L, 10 to the minus 21. That is the key measurement of gravitational waves. So delta L, the displacement, equals 10 to the power minus 21 times the length, 4 kilometers, which is 10 to the minus 18 meters, which is 3 times smaller than the proton radius. This is incredible. So this strain is what I try to predict. And I do. I actually predict the strain from calculations using the 10 to the power 78 gravitons. So from this I infer that gravitons are consistent with the gravitational waves as a quantum gravity theory. I haven't proved they exist, but they're consistent with it.
And do you believe quantum mechanics requires a complete overhaul or just refinements?
Another good question. Thank you for these good questions.
Thank you.
Quantum mechanics has been going on for over 100 years. By the way, it was discovered by a handful of physicists, two handfuls. The usual name: Heisenberg, Bohr, Niels Bohr, Dirac. And as Feynman said, anyone who thinks they understand quantum mechanics is crazy. So after over 100 years, we still don't really understand quantum mechanics. So there are many interpretations of quantum mechanics. So there was a famous paper by Einstein, Podolsky, Rosen, so-called EPR paper in the 30s. And they were concerned about what's called quantum entanglement, that two particles separated by distances can entangle one another in such a way that if you take the spins, up or down spins of both particles, then if the spin of particle A is up and you measure spin up, you immediately know that the spin of particle B is down. So the reason is because in quantum mechanics, what's called the state vector of the wave function is the superposition of both spins. You don't have just one spin or the other. You have superposition to both at the same time. These are called qubits. And so when you do a measurement of the spins, you get what's called an eigenstate, which picks out either what this spin or that spin being the only answer. This is Schrödinger's cat. If you put a cat inside a box and cyanide poisoning, and the cat can be alive or dead. So only when you open the box, it has to be either, they know it's either alive or dead. So this introduced, so John Bell, who was a colleague of mine at CERN when I was a visitor at CERN for a year, a fellow, And I got to know John Bell, and he discovered what's called Bell's theorem. And he showed that through Bell's theorem, if, if quantum mechanics has to be non-local, not local, in order to explain entanglement, quantum entanglement, what Einstein called spooky action at a distance. Because you can't have speed of light faster than it is locally. And so spin A and spin B cannot communicate through faster than light speed, which they should be doing. So anyway, Bell's theorem shows that quantum mechanics is non-local. And by the way, this is one of the reasons I do non-local quantum field theory, because when you extend non-relativistic quantum mechanics, non-relativistic small, weak, slow speeds of particles, to relativistic, to me the natural extension is to go from the non-local quantum mechanics to non-local quantum field theory, which is still causal, by the way. Anyway, so I've been thinking about this issue, and I'm having ideas about the meaning of the eigenstate measurement, where you have just final answers, a bit, not a qubit, one result measurement. For example, in quantum mechanics, you cannot measure the position and momentum with the same accuracy. If you measure the position, total accuracy, the momentum is known with little or no accuracy, and vice versa. So, but when you do the measurement of one or the other, you get either the position or the momentum. So I've been thinking about this, and this is very interesting to do with what's called the double slit experiment for light, which is very fundamental to quantum mechanics. And what does it mean to have a pure eigenstate? Is there a leakage? So I've been looking into this. So back to black holes. In my modified gravity theory, MOG, I published a paper doing MOG black holes, which are not the same as general relativity black holes. And there's now been many papers published on MOG black holes, also by others. And so I call them Schwarzschild MOG black holes and Kerr MOG black holes. So recently I put out a paper where I go back to the first paper I ever published in Cambridge at Trinity College. The first paper was just a mathematical paper where I extended space to Riemannian geometry or pseudo-Riemannian geometry to complex Riemannian or pseudo-Riemannian geometry, 8 dimensions, 4 real coordinates and 4 imaginary coordinates, and the metric tensor is symmetric, the real and imaginary part. So I've gone back to this, and so I put out a paper where I have the inside of the black hole is a complex coordinate pseudo-Riemannian geometry. And by doing this, I can now leverage all of complex variable theory, which you can't do with just real coordinates. And I can do contour integrations in complex variable and remove the singularity at the center of the Schwarzschild black hole and Kerr black hole. So I get a regular black hole. And then I project the complex coordinates onto real space-time coordinates by a projection. So I've also have a paper where I discuss the Hawking information loss paradox, because what information that goes into the black hole cannot come back out. But with a complex variable theory, I can do a complex continuation through the horizon and transport information out and resolve the Hawking paradox. Another paper I have is to do with the James Webb Telescope, because we're now able with the James Webb Telescope, JWST, to see amazingly back into the beginning of the universe. And we can see the first galaxies forming and the supermassive black holes forming. And this is causing what I consider a serious problem, because they've seen galaxies which are only 300 million years old after the Big Bang. Big Bang occurred 13.8 billion years ago. And they see these galaxies are well formed. Stars are well formed with spiral structure. How do you produce a galaxy with such well formed, mature structure in 300 million years? The dinosaurs were on the planet Earth 250 million years ago, and I'm supposed to produce this galaxy in 300 million years. Well, the answer is it's very, very difficult to do this. So I published a paper with a collaborator some while ago to do with supermassive black holes, because the same problem. Supermassive black holes have enormous masses, 10 to the 9, 10 to the 10 solar masses. So you can't produce this object in 300 million years. it's, so then I can only solve it by doing my Mach gravity, because in Mach gravity, gravity's strength is stronger. So when you accrete matter to produce a galaxy or a supermassive black hole, accretion it can be sped up because of gravity is stronger. It's beating the what's called radiation pressure, which pushes the matter out. This is a possible solution. Only if data in the future can determine this, whether it's correct.
Do you think that cosmologists overstate their certainty about the origins of the universe?
The answer is yes. We're back to the straitjacket. How are you going to detect the inflationary model? Because the inflation model states that 10 to the minus 40 seconds after the Big Bang, 10 to the minus 35, 10 to the minus 40 seconds after the Big Bang, the universe expanded exponentially fast. Alan Guth, the American physicist, was first to propose this. And we're never going to detect anything experimentally at 10 to the minus 40 seconds for obvious reasons. So you can't directly detect this idea, which is an interesting idea. And it solves the problem of the horizon problem, because this cosmic microwave background radiation is very uniform. And it's so uniform that 2 points distant from one another in the universe could not achieve this uniform temperature, because the speed of light is not able to reach the 2 points to thermalize the temperature. So inflation does it because it reaches out to the 2 points very quickly. Also, it solves the flatness problem. Observationally, the universe is spatially flat by many observations, cosmological observations. So we can only determine whether inflation is correct through its consequences in late universe. And this is not really enough to say that inflation is the correct model. There are other models called bouncing cosmologies where you don't have inflation. And you can also use them to fit data. For example, the cosmic microwave background power spectrum, which I discussed earlier, very accurate measurements of the power spectrum, which is a very important piece of data, cosmologically speaking. So there are a lot of models about the beginning of the universe, and they're all without a straitjacket. By the way, including mine, I published a paper in 1991 called Variable Speed of Light Cosmology, VSL. And the obvious way to solve the problem with the horizon, 2 points being connected, is to speed up the speed of light. So I had to construct a mathematical theory to explain. You can't just say, oh, well, speed of light is big. So this paper had a rather detailed mathematical structure behind the idea. So at the early 10 to the minus 40 seconds after the Big Bang, like inflation, the speed of light was very large and then quickly became the current speed of light through a phase transition. This is called VSL cosmology. Many papers published about this subsequently. And what is my opinion about it? I published papers showing that the consequences of VSL mimic inflation totally. And but you can't. There are attempts to measure the gravitational waves at the beginning of the universe from the Big Bang, and the bicep 2 measurements some years ago were the first attempts to do this, which the bicep 2 measurements bit the dust because dust obscures the results. And there are efforts underway now to measure these gravitational waves. So somehow they can tell us about the beginning, more about closer to the beginning of the universe. And they're not going to tell us about 10 to the minus 45 seconds after the beginning, but closer to the beginning. So one hopes that they can succeed in measuring gravitational waves at closer to the beginning.
My next question is about the standard model of particle physics. So, is the standard model of particle physics nearing its breaking point?
Now, that's another important question. So I published several papers. I'm afraid I have to keep bringing in my own papers. So there are the standard particle physics model is based on a symmetry groups, SU3 cross SU2 cross U1. SU3 describes the strong interactions, nuclear interactions, called quantum chromodynamics, quarks, the interaction of quarks with particles. SU2 cross U1 describes what's the electroweak interaction, unification of electromagnetism with the weak interactions, radioactive decay interactions. And U1 is the electromagnetic interaction, Maxwell's equations. So the SU3 quantum chromodynamics, you have quarks interacting with one another, and the photon is replaced by what's called a gluon. And the gluon is a massless boson. So in order to get a renormalizable theory, where you cancel infinities, the boson mediating the force has to be massless. Gluon is massless, so SU3 is a gauge theory. You can renormalize it. U1 is electromagnetism, and that produced what's called electrodynamics, quantum electrodynamics. And very successful theory, the most successful theory experimentally. The photon is massless, so it's a gauge theory. You can do renormalization theory successfully. By electroweak theory, the mediating particles are called the W and the Z boson, and they're massive. The W meson is around 80 billion electron volts. So it's not gauge invariant. SU2 cross U1 is not gauge invariant. So in order to make it gauge invariant, you start the theory by making all the masses zero, including quarks and leptons. This gives you a massless gauge theory. It's renormalizable. What happened to the masses? So in this 1964 onwards, it was suggested by Peter Higgs, Kibble, Goralnik, others, and Anderson, the condensed matter physicist Anderson, that in such a symmetry as SU2 cross U1, you can spontaneously break the vacuum of SU2 cross U1 and break SU2 cross U1 down to U1, the electromagnetism, which is not broken, in such a way that the field theory, so-called Lagrangian, of SU2 cross U1, unified theory, electromagnetic unified theory, which was published by Glashow, Weinberg, and Salam, Nobel Prize. This gauge theory is such that even though there are masses now, the theory is renormalizable. 'T Hooft and Veltman, two physicists, another Nobel Prize. However, there are problems, and I'm still working on this. I published 2 or 3 papers on this issue. In order to do spontaneous symmetry breaking, you have to postulate what's called a potential for the Higgs field. The Higgs field is supposed to do the spontaneous symmetry breaking, and it's supposed to produce all the masses of particles. And through the interaction of the Higgs field with all the particles, except the photon, which is massless, of course, and the gluon. So the problem is that the potential for the scalar, the vector, the Higgs boson is formed by knowing the self-coupling of the Higgs particle with itself. So, do we know this self-coupling of the Higgs particle? Straitjacket. The answer is no, we don't. So at CERN, what's called the CMS detector, the muon solenoid detector at CERN, CMS, has been trying to detect the self-coupling of the Higgs particle with itself for years. And the answer is the following, that in order to measure the Higgs coupling with itself, you have a Higgs particle, a real one, and it has to produce 2 or 3 Higgs particles by decay, not because then you have an interaction between 3 Higgs particles or 4 Higgs particles at the decay point. But you can't have a real Higgs decaying into 2 or 3. It violates conservation of energy. So you have to go through what's called a quantum calculation, a quantum loop calculation. So you construct this quantum loop amplitude. And you have to use 2 gluons coupled to a tau, a top quark triangle goes into a Higgs goes into 2 or 3 Higgs. And the intermediate Higgs is called a virtual particle. It can violate conservation of energy. It's not a real particle. But this amplitude is 1200 times smaller than the Higgs decay of one Higgs particle through a W boson or whatever. Problem, it's so small, the amplitude, that it's very difficult to measure. So the experiments have been ongoing trying to measure this. And the answer is we don't even know if the Higgs couples to itself. So the other problem is neutrinos, because the Higgs field is supposed to give mass to all the particles. But in order I'm becoming very technical, in order for the fermions, which are predicted to the Higgs mass, the masses of the fermions are predicted by the Higgs, so-called Higgs mechanism, this Higgs potential, the spontaneous symmetry breaking mechanism. And by the way, the Fermi masses are not predicted, they're just adjusted by hand. Only the W mass is predicted in the Higgs mechanism. So, since we don't know the self-coupling of the Higgs particle, we don't know whether the Higgs mechanism is correct. So in the case of the fermions, spin 1/2 particles, you need what's called a left-handed fermion and a right-handed fermion. And the Higgs particle has to interchange left to right all the time as it's interacting with the 2 particles and the 2 fermions. But the neutrino doesn't have a right-handed fermion. It's never been detected. So the Higgs mechanism does not work for neutrinos to give them masses. So what people do is say, well, it's called a sterile neutrino because a right-handed neutrino doesn't interact with matter at all, only with gravity, which makes it almost impossible to detect. You only detect the right-handed neutrino through what's called neutrino mixing. And experiments have been performed that do not detect the right-handed neutrino as yet. Back to the straitjacket. So I published a paper where I redid the standard model with my finite quantum field theory and redid the calculation of the masses, including neutrinos, and was able to predict the W mass as well as the standard Higgs mechanism. And as for the Fermion masses, all the other particles, there's still an issue about knowing the scale of this non-local behavior of the quantum field theory. I'm still working on this. So again, this is marginalized because all the textbooks do the standard model with Higgs mechanism, not with what I'm doing. But as far as I can tell, no one's discovered anything wrong with my papers. So it's a possible alternative interpretation. Is it correct? The jury's still out. You have to have integrity when you do physics. The jury's out. But still, it means that particle physics is still an open question. There are fundamental questions that have to be solved.
Should we reconsider foundational assumptions about spacetime and causality?
Well, we're back to string theory. The problem with string theory, it has these assumptions about the physics. Another problem is that no one's ever been able to show that string theory produces a standard model, SU3 equals SU2 equals U1, and has many more particles predicted, which we don't detect. So, causality. Well, in quantum field theory, local quantum field theory, there's something called the microscopic causality proof. Technically speaking, two fields, one at x and one at y, when you commute them, the commutator vanishes for space-like separations outside the light cone, which means that two events cannot be connected by speed of light. So therefore the theory is causal. Local field theory is strictly causal. In my non-local quantum field theory, I published two papers, two independent proofs that my theory satisfies the microscopic causality proof. Two non-local field operators commute for space-like separation. It's strictly causal. So for higher dimensions, is string theory causal? Yes, I think depends on how close it is to local quantum field theory.
So, what do you hope your legacy will be, and how would you like future generations to see your contributions to physics?
That's a really tough question. Um, well, it's difficult to speak about yourself as far as legacies are concerned. Uh, it takes time for physics theories that I tend to work outside the box. And I pretty well always. I did a lot of. I had 30 graduate students in my career as a professor. Lots of graduate students, and a lot of the work I did with them was standard, not out of the box, to, so they got their PhDs. But my own work is mainly in collaboration with others, is outside the box. Only through working through outside the box do you hope to make significant progress in physics. You have to move the paradigm, and this is very difficult. And it requires conservative thinking because you shouldn't, as I mentioned earlier, you don't shift the paradigm unless you're really convinced that you should. For example, in history of physics, in 1905, with his 5 celebrated papers, Einstein published the photoelectric effect. He said that electromagnetic fields consist of photons, quanta, Planck's quanta. And he did this through the experiment of the photoelectric effect. So physicists did not accept this. Planck himself did not accept it. Electromagnetic fields made of photons. Niels Bohr did not accept it. And with collaborators, kept publishing papers for years showing why the electric field cannot consist of photons. And eventually, Compton, the American physicist Compton, did the Compton scattering experiment, scattering electrons, photons off electrons. It's called the Compton experiment, which proved beyond doubt that photons exist. And therefore, Einstein got the Nobel Prize for the photoelectric effect. So from 1905 to 1921, no Nobel Prize. Certainly not for relativity theory. He never got the Nobel Prize for relativity theory. So if you're outside the box, it can be a lonely experience. And you have to have a lot of enthusiasm and determination to continue with whatever idea you have. Most ideas in physics are wrong. They just don't fit data. Or they turn out to be incorrect. So if you're outside the box, you're always worrying about your idea turning out to be wrong, which is most likely what will happen. And so we'll see. We'll see what happens.
Yes, I would like to thank you so much for your time, for this wonderful conversation, for your wonderful answers, and it was truly my honor.
Thank you for your questions, which were very good. Each question brings forth important thinking about physics. Thank you.